Hello, I'm your teacher Terry here, and in this video I'm going to describe what our three types of intermolecular forces are, the ones we're going to be dealing with, the van der Waal ones. There's only three types you'll need to know generally in general chemistry, and they pertain to van der Waals intermolecular forces. Van der Waals forces are intermolecular forces between neutral molecules. So there's no charge, no ions here. And this is a nice little diagram here from the OpenStax textbook. It shows that the intermolecular bond, I'll highlight the intermolecular bond is between the two molecules, from one molecule to another. Right? Well, an intra means within. The an intra force or intra bond is between the molecules. So the intramolecular forces hold the molecule together, what keeps it a molecule. But intermolecular forces are these forces between, from one molecule to another one. Okay, so the three types are, here they are. So there's London dispersion forces, and the London dispersion forces are the weakest kind we have. Remember that if you look at my previous video, we had these intermolecular forces between neutral compounds. That's what's happening, not just neutral, but non-polar compounds, and that's what's happening here. So if you look at, say, Br2, bromine, and bromine, how can it be attracted to another Br2 molecule? There's no charges on here at all. But remember, compounds are made up of molecules have electrons around their atoms. And while these electrons are distributed equally throughout this molecule here right now, if you take a snapshot a split second later, maybe some of the electrons are over here, and they're spending less time on the bromine on the left here. If we do that, then this bromine will now have a partial positive charge because it lost electron density. And the other one will have a partial negative charge because it gained electron density just for that moment. Similarly, what would happen if right at the same time, when these electrons moved over here, maybe some of these electrons moved over to the other side? So we have extra electrons here. Whoops, that's wrong color. Oh. So we have, oh, why am I still in red? I can't get off red. Ha! I'm on red for life. There we go. Okay. So maybe these two electrons moved over there. And that would set us up with another dipole. So we'd have a partial positive charge on this bromine and a partial negative charge on this bromine. So these positive and negative atoms will attract each other, and we can set up these are our intermolecular forces between the two of them. So London dispersion forces are these, it's called a temporary dipole because these electrons aren't going to be here for long. They're going to move back. Electrons like to slosh around back and forth. So if we set up a dipole by having electrons move over here, the next moment in time, they're going to go back and they're going to move around. So maybe we'll have, in the next instant, maybe we'll have a totally neutral compound again, where the electrons sort of move back. They're all good, and over time they're going to continuously move back and forth and kind of up and down and all around. And for any split second, there may be a temporary dipole on one bromine or on the other one, which will set up this potential for intermolecular forces between the two of them. Also, when two Br2s collide, if they come together, they collide together, electrons are going to move away from each other, which is also going to set up a temporary dipole. Now, we have an attraction between these two at this moment, but at the next moment, if these electrons go back over here, then the dipole's gone and the intermolecular force is significantly weaker. So these are weaker forces, the London dispersion forces. They're the weakest of the three, actually. They're weaker, and they're due to temporary dipoles due to random motion of these electrons. Okay, so our second type of intermolecular forces we talk about in general chemistry is dipole-dipole attractions. Just like if we had, for instance, HCl. That's quite polar. It's quite a polar compound. We have because of the electronegativity difference between these two, this is a polar molecule, the delta positive on the hydrogen and a delta negative on the chlorine. So this delta positive and delta negative is going to be attracted to another delta positive and delta negative of another one of its molecules somewhere else. So we can set, so the partial negative charge in the chlorine is going to be attracted to the partial positive charge on the hydrogen of another molecule. And this is a stronger one here. We have see this picture here. So the partial negative is attracted to the delta positive of another molecule. And this is going to be stronger because this dipole never goes away. So even though the electrons move around, the electronegativity difference of each atom sets up a permanent dipole. So there's always going to be a partial positive on this hydrogen. There will always be a partial negative on this chlorine. That dipole is never going to go away. Unlike here, some electrons might move over, we have a dipole, but then the next moment the electrons will go back. The electronegativity difference between the atoms is the same. There's zero electronegativity difference, so over time it's completely nonpolar. Here we're polar due to the electronegativity difference. That dipole won't go away, so it's stronger. It's a stronger intermolecular force. So stronger than our London dispersion forces. And it's due to permanent dipoles. Good. And then our third type, it's a special type of London dispersion. It's when you have a dipole with hydrogen. And the key here is that hydrogen, must be bonded to nitrogen and oxygen, a nitrogen, an oxygen, or a fluorine. And we see in this cartoon here, we have water, and we see an oxygen is attracted to the hydrogen. We can draw dipoles here due to the polarity of the water. There's a partial positive charge on the hydrogen, partial negative charge on the oxygen, and then these partial negative and partial positive charges will attract each other. So this is a dipole-dipole interaction. But because it's with hydrogen that's bonded to a nitrogen and oxygen or fluorine, in this case it's an oxygen, it's a very strong dipole attraction. So it's a very strong intermolecular force. So there's a very strong dipole attraction. So it represents the strongest type of intermolecular forces for neutral molecules. The strongest type, significantly more. So the attraction between water molecules will be much greater than the attraction between nonpolar molecules or polar molecules that can't hydrogen bond. And you're saying, well, there's hydrogen here, but the hydrogen's bonded to a chlorine. That's still going to be relatively strong, but the intermolecular force is significantly stronger when that hydrogen is bonded to a nitrogen, an oxygen, or a fluorine. All right, so that's an introduction of our three types of intermolecular forces for neutral molecules, van der Waals forces.